So in magnetic properties, till last class we have just completed diamagnetic material. So the conclusions of diamagnetic material, once again I am trying to recollect back. One, diamagnetism is a universal property, independent of temperature. Even ferromagnetic material will also have the diamagnetic property, but only thing is what dominates higher is that ferromagnetic material, maybe. Diamagnetic materials arises due to paired. So two electrons with opposite spins paired, which means inert gases, for example, best example for this, diamagnetic material. So very less number of lines, I can say zero number of lines will pass through the specimen when applied in magnetic field. In a superconducting stage, almost zero. Almost zero is zero. That is called Meissner effect. I told you. I give any examples. They generally move from stronger field regions to weaker field regions. Paramagnetic substances. These magnets, these materials are weakly attracted by magnets and single, lone pair. Am I right? Unpaired, actually. Unpaired electrons will be there here. So by default, every molecule or atomic stage itself, it's a dipole. It's a dipole. But the only problem is there these uh, uh, dipole moment oriented in random direction in the entire specimen. No, I'll explain. You can imagine that. Say this is the path along which an electron moves. For example. So this is equivalent to a magnetic dipole moment whose moment is in this direction. If it is a direct current, thumb, right hand grip rule, thumb is upwards. Because this is electron, magnetic moment, mu bar is downwards. For one molecule, this is the direction of the dipole moment. For another molecule, it may have a different direction. Due to thermal agitation, they are randomly oriented. The net you ask in any direction is zero. What happens when you apply a magnetic field externally? Some of these dipoles will try to align along the direction of the magnetic field that contributes some net magnetic moment, but it is small, very small. The intensity of magnetization, I know, is very small, very small. Right. I can say relative permeability is greater than 1. Susceptibility is low, undoubtedly. It is of the order of 10 power minus 3 to 10 power minus 5. The only difference between diamagnetic stage and paramagnetic stage is, yes, certain number of lines will pass through this material. When compared to outside, inside number is slightly more. That is the meaning of mu r greater than 1. So, for example, you have cases like sodium, potassium, manganese, aluminum, chromium. Sn means tin, I think, right? And platinum, FeCl3, liquid oxygen, etc. are best examples for paramagnetic material. And this is not universal property. And it is a temperature dependent property. There is a law called Curie's law. According to this law, what you can notice is susceptibility of the material is inversely proportional to temperature. Means if you plot a graph taking temperature in Kelvin, that is the temperature in Kelvin, along x-axis, magnetic susceptibility along y-axis, you will notice that the graph is like this, a rectangular hyperbola. This is what you will call as Curie's law. Okay. So basically, atomic dipoles will tend to align along the direction of the field is a criteria. Next. Next comes ferromagnetic substances. Ferromagnetic substances. Right. See, unlike paramagnetic substances, in ferromagnetic substances, you will find small volume of regions where the entire volume of that particular portion will have a dipole moment in a specific direction, which means the entire volume will have a dipole moment in a specific direction. Such a volume is called a domain. In fact, ferromagnetic substances are identified under this property, domain. Paramagnetic, molecular level, but ferromagnetic substances, domain level. So what are these substances? They are strongly attracted by magnets. They are strongly attracted by magnets. So usually, basically they are solids actually. You cannot have a liquid material with ferromagnetic properties because domain is purely a crystalline property. Crystalline means obviously solids. Right. Next, their intensity of magnetization is very large, positive, and varies non-linearly. What is that I uttered? I will try to express. Agila. Which means in ferromagnetic material, you have seen that the graph is a straight line. I versus H graph is a straight line with less slope, I know. Because as you know, even though I apply magnetizing field, basically very few, less number is oriented in the direction of the magnetizing. But here, it is like a domain behavior. So therefore, you won't see linearity in IH graph. This is saturation, which means even you bring the strongest magnetic field on this planet, this is the maximum that you can magnetize that material. That is called a saturated intensity of magnetization, right? Similarly, one more important point is it's see, in this particular thing, graphs are important, very important. See, this saturated magnetization is again a function of temperature. It varies with the temperature like this. And this temperature is called critical temperature. Okay? below which it behaves like a ferromagnetic material. Thereafter, it behaves like a paramagnetic material. Ferro becomes para. So, therefore, this is a temperature and I graph. Next, its susceptibility is very large. Believe me, it is of the order of 10 power 3 to 10 power 5, very large. And this varies with the temperature. This varies with the temperature. But unlike Curie's law, here susceptibility is inversely proportional to T minus Tc. And remember, this is not Curie's law. This is called Curie-Weiss law. For example, you take iron. Iron, the critical temperature is of the order of 1043 Kelvin. So below this, the material we behave as below this, the material behaves as ferromagnet. Thereafter, it behaves as paramagnet. So Curie's law, even for ferromagnetic material, you are not applying in ferromagnetic state. You are applying that in paramagnetic state. Or here I am not confusing you. You are asking every year. Student ask me one question. I'm posting the same question which you are about to ask. Sir, T, how you will take greater than theta? I am not applying this law for ferromagnetic material ferromagnetic, not in ferromagnetic state. I am applying this in paramagnetic state. After Curie temperature, this temperature is, there is a speciality of this temperature. This temperature is called Curie temperature. Curie temperature. Okay? Actually, what will happen in this, I mentioned a lot of times. That's not. What is actually happening is domain. In ferromagnetic material, imagine that this is a ferromagnetic material. Imagine small volumes in a specimen, a very small volume. This entire volume will have a net magnetic moment in this direction. In this direction. In this direction. In this direction. Within the domain, all that will have the same direction. But neighboring domains, not necessarily they are in the same direction. So in unmagnetized stage, maybe the net magnetic moment is 0. So what is happening in a domain? Like, for example, I can give you examples for this: iron, cobalt, nickel, etc. You will notice this. See, the reason for the domain or the entire magnetic moment directed in one specific direction within that small volume, the reason is spin orbit interreaction. I repeat, spin orbit interreaction between the neighboring atoms within the domain. Within the domain only. Right. Now what happens? Yes, you place this in an external magnetic field. When the material is placed in an external magnetic field, what happens is, now for example, I am taking the sample in an unmagnetized stage. Unmagnetized stage. Now this is the material in an unmagnetized stage. Maybe it is like this. One domain in this direction, another domain in this direction, another domain in this direction, contributing net zero. So this is unmagnetized state. Okay. For example, in the absence of the external magnetic field, you are asking me, can this domain influence that? No. Why it is like that? Spin orbit interreaction of the neighboring atoms. But there is no such interreaction between these. If there is such interreaction, why they exist as two different domains? It should not be like that. It should entirely be one single domain. Right now. Two things are possible when I am applying an external magnetic field. When I'm applying external magnetic field, two things are possible. One is, see, something like this. I've applied magnetic field like this, for example. Okay. One is like this. What is this, domain growth? You're asking the same. The entire property expands. The domain volume expands. Means neighboring regions are merged into this domain. So that the entire volume will have a specific direction based dipole moment. Another way, depending upon the strengths, relative strengths, material, any of these two things are possible. So in the first case, the walls were moving, domain walls were moving. In the next case, in this case, oriented like this, maybe orientation reoriented, staging the same. This comes under magnetization by domain rotation or orientation. So either of these two things will happen. Okay. Now, what is basically the best examples? I said iron, cobalt, nickel, and their alloys. They are the best example. This property is strictly exhibited by crystalline solids. Right. That's it. And one more important point is what I am now discussing. It's not in main syllabus. Main syllabus. I think hysteresis. I heard that they have, as per my knowledge, they have removed that in the present syllabus. But I just want to take confirmation from you. Otherwise, I'll just give you a brief introduction about that. Now you have understood clearly. Now you have understood clearly that if I plot a graph taking magnetizing field along x-axis, intensity of magnetization along y-axis, you noticed that saturation is happening, right? This is the saturation. Beyond this, whatever you raise, nothing happens. It is brief introduction. Now what will happen is, now if I am reducing the magnitude of this field, you know what will happen? It won't follow the same path. This lag is called hysteresis. Now it will intercept here. You know what is the meaning of this interception? Here OC represents retentivity, which means certain magnetization is left permanently with the material. Okay. Now I want to remove even that. So what to do? Tell me. To remove that, what to do? You apply field opposite direction. So what happens is, now again it will intercept here. D. OD refers to coercivity. So that is the magnitude of the magnetic field required, magnetizing field required to permanently demagnetize the material. And again, you keep on increasing in that direction. What happens? You will reach some stage like this again, in that direction. Right. Again, you follow the same path. This loop is called hysteresis loop. So what is the significance in hysteresis loop is OC, OD, retentivity, coercivity. And the area gives loss per cycle. Loss, purely loss. Every cycle, the loss. Even elasticity also, you will face the same situation. Area provides loss. So now the issue is that this will allow one important observation. See, again, the loss is also two ways. Loss measured in SI units. This is mu naught times area of IH loop in SI system. In CGS system, it is simply 4 pi times area of IH loop. So in which units they are asking, accordingly you should take a call. Again, on the basis of three factors: retentivity, coercivity, hysteresis loss. Hysteresis loss. This is called hysteresis graph. Materials are classified into two categories. One, soft magnetic materials. Two, hard magnetic materials. So what are their identity? They will have low retentivity, low coercivity, and small hysteresis loss. ఇది ఎలా ఉంటుందంటే మీ భాషలో చెప్పాలంటే it is like this. అన్ని లోనే చూసుకోండి. హార్డ్ మ్యాగ్నెటిక్ మెటీరియల్, హై రిటెంటివిటీ, high coercivity. హై రిటెంటివిటీ, హై కోయర్సివిటీ ఎప్పుడైతే ఉంటుందో ఆటోమేటిక్గా లార్జ్ హిస్టీరిసిస్ లాస్. అది ఎలా వస్తుంది అంటే గ్రాఫ్ ఇది హైయే, ఇది హైయే, కాబట్టి ఏరియా హై. రైట్. సో వాట్ ఈస్ ది significance of this classification? Remember, when you are using electromagnets, core material of electromagnets, okay, and cores of transformers, motors, generators, etc., you require this property. Less loss, వేడెక్కిపోతుంది transformer. So what are example for this? Soft iron is one example. There is a metal called mu metal, stelloid. These are examples of ferromagnetic materials which comes under soft magnetic materials. Whereas for permanent magnets in speakers, you require this. For preparing permanent magnets in loudspeakers, various electric meters, you require this. The ammeter undi, you have horseshoe magnet. Voltmeter undi, you have a horseshoe magnet. A moving coil galvanometer, you will have a horseshoe magnet. You require permanent strongness in that. Okay. ఎందుకు మీరు ఇప్పుడు the constant of the instrument should remain constant forever. అదేంటో అలా చూస్తాను. C theta is equal to BIAN. అంతేనా? మూవింగ్ కాయిల్ గ్యాలనోమీటర్. ఇప్పుడు theta by I called sensitivity. సెన్సిటివిటీ ఏమవుతుంది? బ్యాన్ బై సి. అందులో నెంబర్ ఆఫ్ టర్న్స్ మారవు, ఏరియా మారదు, సి కూడా పెద్ద చేంజ్ అవ్వదు. చేంజ్ అయ్యే ఛాన్స్ దేనికి ఉంటుంది? బీకి ఉంటుంది. సో ఇప్పుడు కోయర్సివిటీ ఎక్కువ ఉంది, రిటెంటివిటీ ఎక్కువ ఉంది, ఏమవుతుంది? ఇట్ వోంట్ చేంజ్ మచ్. రైట్. వాట్ ఆర్ ద మెటీరియల్స్? స్టీల్, alnico, alcomax, tinconal. These are the best example for ferromagnetic materials of this kind. With this, I have completed the theory related to magnetic properties. Opposite direction. For example, if the field is from left to right in a solenoid, you change the direction of the current, the direction of the field inside the solenoid will now become right to left. What is repeated in the upward part is repeated here. కింద పడతాగా నువ్వు ఆపోజిట్ డైరెక్షన్ లో ఫీల్డ్ డిక్రీజ్. సి ఫర్ ఎగ్జాంపుల్ కరెంట్ తగ్గించుకుంటూ వస్తున్నావు సోలినాయిడ్. సో ఇట్ హెచ్ విల్ decrease will reach here. H. Now you are changing the direction and increasing the magnitude. It will go like this. What you have done here, you have repeated here. These are all previous mains questions. And now, what is the objective of this class? And now, on behalf of you, I am completing PYQs. So if these PYQs are done, implies your preparation in this part is also done. Right? Yes. You see, majority of the questions you will answer because mostly they are theory type. Given below are two statements. One is labeled assertion, the other labeled reason. Okay. Magnetic monopoles do not exist. True. Only charge exists, mono charge, plus or minus, but magnetic monopoles do not exist is a correct statement. Magnetic field lines are continuous and form closed loops. Correct. Electric field lines are not closed loops. They start at a positive charge and end at a negative charge. If there is no negative charge, they'll travel till infinite. You will draw lines till infinite. They are open curves, whereas magnetic field lines are closed curves. So therefore, both A and B are correct, and in fact, the correct explanation is because magnetic field lines are continuous and closed loops. So once it is closed, it means one phase will become north side, the other phase becomes south side. Any doubts? Clear? Got the point? Right. See, if they are not closed loops, isolated poles exist. See, for example, you take isolated charge, they are not closed loops. You can see open. They are open. If it is not open, if it is closed, means an identical polarity exists somewhere. So which means monopole do not exist. Next. A magnetic moment of a bar magnet given M given suspended uniform magnetic field B given work done in rotating it from the most stable to most unstable. Remember, B M is called stable position. In this case, potential energy is minus MB. Most unstable position. This is the most unstable position. The final potential energy is plus M. The work done is 2M. So 2 times 1 by 2 into 8 into 10 power minus 2. So the answer is 8 into 10 to the power of minus 2 joules. Direct formula. Next, susceptibility of a paramagnetic material is 99. Can you please help me writing this relation? Mu r is 1 plus susceptibility. This is 100. Okay. The permeability of the material is, or mu is mu r times mu naught. So therefore, 100 into 4 pi into 10 to the power of minus 7. So this will be 4 pi into 10 to the power of minus 5. మీకు యూనిట్ కూడా గుర్తుపెట్టుకోవాలి, హెన్రీ పర్ మీటర్. ఓకే, రైట్. ఎలా గుర్తుపెట్టుకోవాలి సార్ అంటే వెరీ సింపుల్. మ్యాగ్నెటిక్ ఫ్లక్స్ ని ఇలా కూడా రాసుకోవచ్చు, హెన్రీ పర్ యాంపియర్ కదా. ఇది మ్యాగ్నెటిక్ ఫ్లక్స్ యూనిట్స్ ఇవి, దీని నుంచి మ్యూ తెచ్చుకోవచ్చు కదా. రైట్, హెన్రీ పర్ మీటర్ గుర్తుపెట్టుకోండి. రైట్. మ్యాగ్నెటిక్ ససెప్టబిలిటీ ఆఫ్ ఎ మెటీరియల్. అరే ఇప్పుడు ఆ పై క్వశ్చన్ చేస్తే కింద క్వశ్చన్ చేయగలరా లేదా చెప్పండి. 2021లో ఈ క్వశ్చన్ అడిగారు, 2022లో ఆ క్వశ్చన్ అడిగారు. ఇక్కడ ఏం తెలుస్తుంది మీకు? మ్యూ రిలేటివ్ ఈజ్ 1 plus 499. దిస్ ఈస్ 500. ఓకే. పెరిమిబిలిటీ ఇన్ వాక్యూమ్, మ్యూ కట్టేయచ్చు. మ్యూ ఆర్ టైమ్స్ mu is equal to mu r times mu naught. So 500 into 4 pi into 10 power minus 7. This is 2 pi into 10 power minus 4 Henry per meter. Any doubts, boys? Right. Diamagnetic property depends on temperature. Wrong. Induced magnetic dipole moment in a diamagnetic sample is always opposite to the magnetizing field. Correct. 1 incorrect, 2 true. Right. Soft iron is a suitable material for making an electromagnet. Don't get confused. This is asked in 2022. That time it was in the syllabus. Right. This is because what is the significance of soft iron? Low coercivity, low retentivity. Low coercivity, low retentivity. See, if you have a doubt, low coercivity, high retentivity is a wrong option. Okay. Low coercivity, low permeability. See, obviously, identity of ferromagnetic material is they will have very high permeability. Identity of ferromagnetic material is they will have high permeability and low retentivity. Correct? చాలా మంది క్వశ్చన్ అప్పుడు చేయలే వాళ్ళకి ఏం గుర్తుంది లో కోయర్సివిటీ లో రిటెంటివిటీ ఆ లో కోయర్సివిటీ లో రిటెంటివిటీ కాంబినేషన్ లేదని వదిలేశారు ఈ క్వశ్చన్ ఇప్పుడు బేసిక్ గా ఇట్ ఈస్ ఎ ఫెర్రోమాగ్నెటిక్ మెటీరియల్ ఐడెంటిటీ ఏంటి మ్యూఆర్ నెక్స్ట్ ద ఫెర్రోమాగ్నెటిక్ ప్రాపర్టీ డిపెండ్స్ ఆన్ టెంపరేచర్ at high temperature ferromagnetic becomes a paramagnet. This is a true statement. At high temperature, the domain wall area of a ferromagnet increase అయితే paramagnet ఎందుకు అవుతుందా? So this is wrong. So statement 1 is a true, statement 2 is a wrong. Right. Ashrita. You know, right. And T35%. Mu r is 1 plus susceptibility. Susceptibility is mu r minus 1. Mu by mu naught minus 1. Any doubts? Boys and girls? Clear? Right. Next. ఇప్పుడు ఆ క్వశ్చన్ రోహిత్ నిన్న మనం చదువుకున్నది దాటి నీకు ఇప్పటిదాకా క్వశ్చన్ ఏదన్నా తగిలిందా? A solenoid having area A and length L is filled with a material having relative permeability 2. The magnetic energy stored in the solenoid is ఒక్క నిమిషం. See, B square by 2 mu naught is the expression for energy stored per unit volume. Actually, energy stored per unit volume when if air is the medium. Air in a medium, B square by 2 times mu r mu naught into volume. That's all. Any doubts? Boys and girls? Right. The percentage increase in magnetic field P when space within a current carrying solenoid is filled with magnesium are B proportional to mu r. You know that. Solenoid B is equal to, what is the general formula? B is equal to mu naught Ni. Okay. Now in material, mu r times mu naught Ni. So mu r minus 1 by 1. అంతేగా బాయ్స్? పర్సంటేజ్ అంటే ఇదే కదా. D dash minus B by B is mu r minus mu naught by then mu r mu naught minus mu naught by mu naught. ఇదేం వస్తుంది? Mu r minus 1 by 1. In fact, this is susceptibility. That is the susceptibility. 1.2 2 into 10 power minus 5. జనాలు ఇక్కడ వచ్చాక ఈ లేదని ఆప్షన్ వెళ్ళిపోతారు. 1.2 is nothing but 12 by 10, 6 by 5 into 10 to the power of minus 5 into 100%. ఇప్పుడు ఇదేమవుతుంది? 6 by 5 into 10 power minus 3%. I still know some students who did not do this question, even though they know this formula. So in the process of doing 1.2 into 10 power minus 5 వచ్చి అక్కడ మనకి 5 వచ్చింది, అక్కడ 3 వచ్చింది అని ఒకళ్ళు. అంటే 1.2 6/5 అని చూసే ఓపిక లేకపోతే అంత టైం స్పెండ్ చేయలేను. ఇప్పుడు ఇది చెప్పండి, ఈ క్వశ్చన్ మిస్ చేసుకున్నారంటే వాళ్ళు లాస్ అయినట్టేదా కాదా? ఎన్ఐటి వరంగల్లో ఈసీఈ రావాల్సిన వాడికి ట్రిపుల్ వస్తుంది ఒక క్వశ్చన్ ఛాన్స్. ఆలోచించండి, జీవితాంతం ఆడవాలి. రైట్. నెక్స్ట్ క్వశ్చన్. బార్ మ్యాగ్నెట్ ఆఫ్ టోటల్ లెంగ్త్ 2L, 20 units, and the field at point P is at a distance D is equal to 10 units from the center of the magnet. If the relative uncertainty of length measurement is 1%, the uncertainty of the magnetic field at P is. Actually, the problem with this question is the length part is crucial. The magnetic moment formula which we have applied do not contain the length term. Why? Because at that time we took the condition D much greater than L. But this is a comparable. So in that case, you need to know if length is comparable, what formula to have. Electrostatics, you have that relation. In electrostatics, you have that relation. I think, if I am not mistaken, the magnetic field formula contains mu naught by 4 pi capital M by 1 minute D square plus L square whole to the power of 3 by 2. If I can, that's the relation. D square plus L square whole to the power of 3 by 2. If I'm not mistaken, this is the relation. The uncertainty అంటే dB by B మిమ్మల్ని ఎంత అని అడుగుతున్నారు, percentages. Magnetic moment term contains one length term. సింపుల్ అండి. dB by B లో delta M by M plus delta by D square plus L square whole power 3 by 2 times D square plus L square whole to the power of 3 by 2. Remember, here you will have 1%. Here you will have 3 1%. If I take D square plus L square under root as some Z, remember this is again a Z term. That is a length term again. So cube power 3 we have. So therefore, obviously this will become 4%. That is how you should identify. Or you do, you'll get the same answer. Next. In fact, never it happens, this percentage will come. You may confuse between 1 and 3 options. These possibilities are not there. The coercivity of a magnet is 5 into 10 power 3 ampere per meter. Remember, this is 2024 question. 2024 ante not this year, last year. That syllabus, this syllabus is slightly different. The amount of current required to pass in a solenoid of length 30 centimeter, number of, so that the magnet gets the, you know what they have given? They have given H. They have simply given H. E is equal to mu naught H. And then the amount of current required, mu naught N by Li is mu naught H. Cancel. The current is H 5 into 10 to the power of 3. Length enta 30 into 10 power minus 2. By number of turns enta 150. So the answer is 10 amps. Who will do this question? Those who know this formula, they will do this question. 10 power 3 ampere per meter. ఒక్కోసారి చేసేది ఏమవుతుందంటే చూసుకోకుండా ఆ 10 power 5 into 10 power 3ని mu naught అనేది ఈక్వేట్ చేసేస్తాం. పోతుంది ఆన్సర్. నెక్స్ట్, the free space inside a current carrying toroid is filled with a material of susceptibility so and so. అది paramagnetic material అయి ఉంటుంది. The percentage increase in the value of the magnetic field inside the toroid is whatever it is, B is proportional to mu R. So delta B by B is same, mu R minus 1 by 1. Here, mu R susceptibility, mu R at 1 plus susceptibility. 1 plus susceptibility minus 1 by 1. Susceptibility. Susceptibility is 2 into 10 power minus 2. Remember fraction. Percentages into 100. 2%. Any doubts? Toroid అయితే ఏంటి, solenoid అయితే ఏంటి? ఫైనల్ గా న్యూమరేటర్ లో mu term ఉంటుంది. mu అంటే mu or mu naught అప్పుడు. Any doubts? 19th question. Any doubts? Right. It is already a paramagnetic substance align themselves along the direction of the external magnetic field. Opposite ga kaadu kada, dialogue kaadu. Next, attract strongly. Wrong. Has a susceptibility slightly more than 0. Correct. Move from a region of stronger field to weaker field. Wrong. Adi diamagnetic. Only 2 correct options. Wrong kottedappudu you need to know what is the reason for. Okay. Attract strongly towards external magnetic field. Enduku kottesa? That is the property of ferromagnetic material. Alane move from a region of stronger to field kottesanu. Why? That is the property of diamagnetic material. Next, diamagnetic substances ke susceptibility ante kada opposite direction kada, -1 నుంచి 0 మధ్యలో ఉంటుంది. Correct. Diamagnetic substances when placed in external magnetic field tend to move right. But year less than or equal to ne ichadu. But honestly speaking, the relation. Wait. అది అంత సీరియస్ గా చూస్తే పోద్ది. Given below are 2 statements. Susceptibility of paramagnetic and ferromagnetic substances increases with decrease in temperature. Correct, because they obey temperature law. Diamagnetism is a result of orbital motion of electrons developing magnetic moments opposite to the applied field. Correct. Electric mono, చూడండి, ఇదేమో 2021లో అడిగారు, మొన్న 2025లో కూడా క్వశ్చన్ అడిగారు. ఎలక్ట్రిక్ మోనోపోల్స్ డు నాట్ ఎగ్జిస్ట్, రాంగ్. అంతేగా. మ్యాగ్నెటిక్ ఫీల్డ్ ends due to solenoid at its ends and outside cannot be completely straight and confined. Magnetic field lines are completely confined within a toroid. Magnetic field lines inside a bar magnet are not parallel. ఇది కూడా డౌటే. psi is equal to -1 is the condition for a perfect diamagnetic material in superconducting stage లో ఇదేగా ఎక్స్పెల్ చేసేస్తుంది అని. కాబట్టి there is no doubt in this. ఇది తీసుకోవచ్చు. దిస్ ఈజ్ ఎ స్పెషల్ కేస్ కదా, సూపర్ కండక్టింగ్ స్టేజ్ లో ఎక్స్పెల్ చేసేస్తుంది, జీరో అయిపోతుంది కదా. దట్ ఈజ్ ఓకే. పర్ఫెక్ట్ డయామాగ్నెటిక్ మెటీరియల్. ఇప్పుడు ఈ పక్కా కరెక్ట్, సి పక్కా కరెక్ట్, ఈ రెండు ఆప్షన్స్ పక్కా కరెక్ట్. మిగతా ఏవి కాంబినేషన్స్ లో గొప్పగా లేవు. ఫర్ ఎగ్జాంపుల్ మ్యాగ్నెటిక్ ఫీల్డ్ లైన్ ఇన్సైడ్ బార్ మ్యాగ్నెట్ ఆర్ నాట్ ప్యారలల్ అంటే నో ఐడియా. ఇన్సైడ్ లోపల ప్యారలల్, ఎడ్జెస్ దగ్గరకు వచ్చేటప్పటికి పోద్దిగా. ఇన్సైడ్ అంటే ఉద్దేశం నాట్ ఎట్ ద ఎండ్స్ అని అనుకుంటే ఓకే, రైట్. Magnetic field lines due to a solenoid at its ends and outside cannot be completely straight and confined. Actually, to some extent, B is also okay. But NCERT-లో డయాగ్రామ్ ఉంది, ఆ డయాగ్రామ్ చూస్తే బికి కొంచెం డౌట్ వస్తుంది. ఒకసారి నేను చూపిస్తాను. అంటే సి అండ్ ఏ డామినేటింగ్లీ కరెక్ట్ కాబట్టి యూ షుడ్ గో ఫర్ దట్ ఆప్షన్. అబ్జెక్షన్ పెట్టినా ఇదేది అది. వాళ్ళు బి అండ్ డి కూడా కొంతమంది పెట్టారు ఇలా. సాఫ్ట్ ferromagnetic material is placed in an external magnetic field. The magnetic domains may increase or decrease in size and changes its orientation. కరెక్టేగా, ఇప్పుడే చెప్పాను. నెక్స్ట్, a paramagnetic substance shows a net magnetization of when it is placed in an external magnetic field of so and so temperature. At this temperature, at a temperature 0.4 magnetic field of 0.4 Tesla at a temperature of 4 Kelvin. When the sample is placed in an extra, అసలు ఏమేమి ఇచ్చారనేది ఒకసారి ఐడెంటిఫై చెయ్యండి. .3 Tesla at a temperature, the magnetization will be. నెట్ మ్యాగ్నటైజేషన్ ఐ ఇచ్చారు. ఓకే, ఇప్పుడు ససెప్టబిలిటీ మామూలుగా అయితే I/H, which is proportional to I/B, and this is also proportional to 1/T. So I1 T1 by B1 is equal to I2 T2 by B2. ఎనీ డౌట్స్? చూడండి, నేను ఇక్కడ చేసేది దేనికోసం మీకు చెప్పడానికి కాదు, మీ ప్రిపరేషన్లో నాది పార్టే. ఇక్కడ ఇది అయిపోతే యూ డోంట్ రిక్వైర్ టు గో త్రూ దిస్ అగైన్. I1 అంటే ఎంతరా? 6. T1 అంటే 4 Kelvin. B1 అంటే 0.4. I2 అదే కట్టాలి. T2 24 Kelvin. B2 0.3. ఇది 3 6 3 6 3 8. So I2 is 3/4.75 ampere per meter. 6 ampere per meter ఉండే ఇంటెన్సిటీ ఆఫ్ మ్యాగ్నటైజేషన్ 0.75 పడిపోయింది. ఎందుకు? టెంపరేచర్ ఫ్యాక్టర్ డామినేటింగ్. ఎనీ డౌట్స్? కెల్వినే తీసుకోవాలి. నెక్స్ట్, a bar magnet dropped through a metallic cylindrical pipe takes more time to come down compared to non-magnetic bar which same jam. Yes. Why? Due to eddy currents. Eddy currents. For the magnetic bar, eddy, other reason on the kenda. Eddy currents are produced in the metallic pipe. Right. Correct explanation kuda. ఇప్పటికి ఈ మోడల్ ఎన్నిసార్లు అడిగారు? సేమ్ క్వశ్చన్ ఎన్నిసార్లు చేసాం? మోడల్ క్వశ్చన్ కూడా సేమే అనుకుంటా నాకు తెలిసి. ఓన్లీ డిఫరెన్స్ ఏంటంటే ఫ్రాక్షన్, అక్కడ పర్సంటేజ్. ఇక్కడ ఏముంది? μr - 1/1 అంతే. అంటే ససెప్టబిలిటీ బై 1, 1.2 × 10⁻⁻5. సేమ్ క్వశ్చన్ ఇందాక పర్సంటేజ్లో అడిగారు. ఇప్పుడే చెప్పాను నేను ఆ క్వశ్చన్. 6/5 × 10⁻³ పర్సంటేజ్. సేమ్ క్వశ్చన్. ఎస్, ఒకసారి వస్తున్నా. దీనిలో మ్యాగ్నెట్ పడేసారు. విత్ జీప్ రాదు, లెస్ దాన్ జ్యూస్, ఎక్కువ టైం పడుతుంది. ఇప్పుడు ఇక్కడ బయట ఒక రాయిని పడేసాం, ఇక్కడ మ్యాగ్నెట్ రిలీజ్ చేసాం అనుకో, ద స్టోన్ విల్ రీచ్ ఫస్ట్ బిఫోర్ ద మ్యాగ్నెట్ డ్యూ టు ఎడ్డీ కరెంట్స్. ఓకేనా? Now please give me feedback. Is this okay? Fine. Any doubts? Your entire magnetic properties, including theory, is done.